All right, everybody, welcome back. This is time for our third of four lessons in this particular unit about types of waves, waves characteristics, how we classify them, a little bit more specific about kind of more traditional waves, typical kind of sine wave things, a little bit less about the periodic motion, harmonic motion, and more into the like what the hell's a wave kind of thing. A couple of things. First thing first, the first couple slides here are about a couple of different ways that we classify waves. There's lots of different ways to talk about them. Some, like this particular one, is based on the type of medium, and the other one on the next slide is kind of more about how they move. There's other ways as well to classify waves. There's no particularly right or wrong way, but there's a couple of different styles that we use. So for the first one here, the key idea here is to classify waves based on the type of medium they have. And so in order to understand this part, obviously you need to know what a medium is. And that's kind of the key vocab word. Whoa, hello. That's the key vocab word that's, come on back, that's relevant for this one. So the term medium here in its, vocabness means the material that the wave is traveling through. And that's the basic idea behind what a medium is or what it means. So let me see if I can get this working here. Is that going to go too wide? Come on, friend. Let's do your thing. There we go. Medium, what the material is traveling through. So there's a couple of big ideas. So for example, if you're talking about a seismic wave, which is an earthquake wave, if you're not familiar with that term, the medium of that would be a solid. If you're talking about a water wave, the medium of that would be water. If you're talking about typical sound waves, typically sound waves medium is traveling through air. Although you know that if you take sound and you move it into a different medium, it definitely sounds different. So for example, if you've ever tried to talk to somebody in the pool underwater, sounds sound different when they're going through a liquid medium than when they're going through a gas medium. And similarly, if you're trying to talk through sound waves are traveling through a solid, that also sounds different. So, if someone's talking, you put your ear down to like the table, or even sometimes, like I notice with headphones, you can hear the vibration through there. It's kind of why your voice sounds different in your head than it sounds in recording. So like when you listen to your own voice on the phone or on the computer, it definitely sounds different because your voice is just traveling through air, as opposed to what you hear, it's actually traveling through, meat and bones and stuff. It sounds different inside your head. So medium is the material that it's traveling through. When we classify waves according to medium, there's two basic ideas about what the two categories are. There's waves that we call mechanical waves, and then there's electromagnetic waves. The big key difference here is that mechanical waves require a medium, electromagnetic waves do not. And that's one of the big, easy differences between these two. Electromagnetic waves are what you see down in this big diagram that's down here. Typically, what you consider to be light is an electromagnetic wave. And there's lots of other things that fall into this category as well. Electromagnetic waves do not require air or water or a solid to travel through. Otherwise, it would be awfully dark here because light has to get from the sun to the earth, and it has to be able to do that through space across vacuum. Electromagnetic waves have some other unique characteristics to them as well. And you can kind of see some of them in this little diagram over here, which is a little bit unique. I'm not going to test you on that or anything, but sometimes students ask me why they're called electromagnetic waves. And it's the concept that electrical waves and magnetic waves are sort of operating at right angles to one another, that whenever you have electromagnetic radiation, it has aspects of both electric field and a magnetic field, and that those things do operate literally at 90 degrees to each other. One's up, down, one's left, right. So they're part of kind of two sides of the same coin, or maybe like they're the sides and the edge of the same coin. I want to talk about that. But with electromagnetic waves, again, key idea, really important thing about electromagnetic waves down here, write this down, is that electromagnetic waves can travel through a medium, but do not require a medium to travel through. Furthermore, they're all related to one another in the sense that electromagnetic waves all travel at the same speed. And it doesn't matter a lot what speed they travel through, because the speed's huge, and I'll get to that in a later slide. It does matter. Like if you take light and you travel it through space versus air versus water versus say glass or crystal, it does definitely change it. But all electromagnetic radiation has basically the same speed and it's ridiculously fast. Mechanical waves on the other side do require a medium. They have to travel through something. They can't just travel through space, and they're generally quite a bit slower. And they can have very different types of speeds depending on what they are. So sound waves travel at a very different speed than certain types of seismic waves travel at a different speed than, say, water waves. So they all have a different kind of range in terms of what they do. And then the medium strongly affects the speed of mechanical waves in terms of what they're doing. So mechanical waves, usually it's mechanical, they use that phrase because it's a wave that's traveling through stuff. Electromagnetic waves usually not necessarily traveling through stuff. They can, but it's not as required. So key difference between those two. Okay, second way that we can discuss waves and how they work has to do more with sort of how we draw them and how the material or the medium is interacting with the direction of wave travel. Now, this is a little bit weird. The easiest way to picture this is with a slinky and thinking about how a slinky works. There's two main ways to make a wave in a slinky. There's the typical kind of left, right, whipping it back and forth wave. And then there's the shove it forward, pull it back kind of wave. And these have two very different ways of moving. So what I want you to kind of be thinking about is if you had, say, for example, a little teeny tiny, like a little ribbon or something that was attached, a little flag that was attached to that slinky in one little spot so that you could kind of watch what was happening. If you think about what's happening in this wave, as you shove it forward, you can see that wave pulse travel from basically left to right across the field. It would go, or whichever direction it was going, the energy would be traveling. That'd be the direction of the wave pulse. You could see that little compression move through the wave. But the slinky pieces themselves would literally move like this. Even though the wave pulse is traveling end to end, all the way one way to the other, each little bit is only moving a tiny part. So the key here with compression waves or longitudinal waves is the other name for these. And you can see those names are written up here. That this type of wave is that the wave energy transport, the direction of the wave pulse and the direction of the medium are basically in the same plane. They're both in, say, the Y dimension or the X dimension, whatever that is. That, again, if the wave pulse is going from one side to the other side, and then the little pieces of the wave are just moving from left to right as well, we would consider that to be a compression wave or a longitudinal wave. Sound waves are the classic example of a longitudinal or a compression wave. Certain types of seismic waves are also compression or longitudinal waves, and that's a really important thing to know. Sound waves or compression waves. Transverse waves, on the other hand, this is that side-to-side motion. So with the side-to-side motion, think about what you're doing is that if you make a whip in a slinky, like if you're talking about this diagram here with these two hands, the hands are moving up and down. So you're making that whip motion. But the motion of the wave pulse is still this direction, even though your hands are moving this direction. So again, if they're at right angles to one another, so you've got the direction of the medium, the direction of the medium is going this way, but the direction of the wave pulse is going this way. That's called a transverse wave because those two motions are across, or trans, that's what that word means. They're across from one another at 90 degrees to each other. So again, if you think about what this little flag would do on this, is that even though you could watch the pulse move down, the little flag is literally just going to move up and down in one spot. So again, because they're right angles to each other, they are transverse waves. So from that previous slide, you may already recognize that electromagnetic waves are transverse waves. They're actually kind of multiply transverse waves. They've got the wave pulse going this way, an electric field and magnetic field. So they've actually got several different types of transverse going on. But then there's other types of ones. Your typical sine wave as you draw it is usually drawn as a transverse wave. A lot of times how we draw waves is in that transverse wave format. And then certain types of seismic waves, water waves tend to be transverse as well. Again, you can imagine a little splash in water and there's a little duck that kind of floats up and down. So water waves tend to be transverse waves. They're not really compression waves, although you could probably come up with some way to think of a compression wave that would work for that. So again, are just kind of two main ways. So here's your job. Take a second, and I want to see if you can kind of classify each of these different images here as being either mechanical or electromagnetic. And then second of all, can you categorize them as being either transverse or longitudinal? Again, just to practice using that vocab which of these images represent mechanical waves versus electromagnetic waves, and which of these represent transverse versus longitudinal waves. There's my cat's tail is in there if you're wondering what that little flicker is. Okay, so water waves. If we're talking about this picture up on the top right here, this one is a mechanical wave. It's a water wave, so it does require a medium. And this would be, because of the way that these little wave pulses are moving left to right, this would be considered to be a transverse wave. Okay, the second picture right here, we're talking about the sun rays, I guess that's light. That would be an electromagnetic ray. Again, does not require a medium, although there is a medium present here. It's traveling through air, but electromagnetic rays do not require, so they are that style. And then again, we talked about this, electromagnetic waves are transverse waves. Again, they tend to have those two different things moving, the side-to-side wiggly motion. For here, Indiana Jones, I was thinking about the motion up in his whip, in terms of what that was. So if you think about a whip and cracking that whip, first of all, that would be a mechanical wave. It has to be traveling through something. There's no way to have a crack in a whip without the whip. It's got to have a medium. And then it would also be considered to be a transverse wave. Again, you've got that typical kind of sine wave version to it. All right, we got a slinky wave over here. So this particular slinky wave would be a mechanical wave because there is a medium and it does have to have a medium to travel through. And in this particular case, you can see that little compression coil here. This part of it right here would be considered to be a longitudinal wave. Although if you want to take a look at it and go, yeah, there's a little bit of transverse in there, that's fine. The main part of this energy, though, is going this direction. So if it's going, across that way, and you've got the little compressions are right here, that would be considered to be a type of a longitudinal or compression wave. This one right here is light traveling through a medium, and here you can actually see that the light is bending a little bit and changing its speed as it travels through these different media. It's traveling through air, and then through a prism or a crystal, and then back through air again. So this is an electromagnetic wave, and it is a transverse wave by definition. And then right here, you could answer this two different ways, I guess, if you want to. You could either be talking about directly about the motion of the strings themselves, which are strumming this way and then they're wiggling this way, or you can be thinking about what's happening in the air itself. So if you're thinking about the fact that this is a guitar, you can kind of be thinking about it. If you pluck it, that wave travels to one end. It has some components of transverse to it. But if you think about the way this is moving this direction, you strum it this way and it moves this way, you could also be interpreting this as being longitudinal. And then finally, if you want to talk about this as being the sound that's being produced rather than the wave itself, the string itself is more transverse, but the sound, the way it's making the air vibrate around it, actually is longitudinal. Again, sound waves are longitudinal. That's going to be an important piece, or compression waves, an important piece to kind of remember as you move forward. All right, moving on. What am I doing? Too many. Okay, so some vocab time here as we're trying to talk about these different wave characteristics and some words that we use to describe these wave characteristics. We're going to use a real traditional transverse sine wave form like this to talk about pretty much all kinds of waves. We can even take longitudinal waves and talk about them using a form that's like this. You've seen this even with in the other videos on how a pendulum moves, how a spring moves. A very, very common waveform to use a simple sine wave transform wave shape to talk about it. Very common, sorry, cattail. So the couple vocab words they need to get. Number one, crest and trough should be relatively straightforward. A crest would be considered to be a peak area. Let me get a pen here so I can actually figure out what I'm doing. There we go. Give me a pen. Give me a pen. There we go. A peak would be an area at the top like that. A trough would be an area at the bottom like that. So an up versus a down. These do have different meanings depending on whether they're sound waves or light waves. So it doesn't matter whether it's up or down. They're not just opposite sides. Like in sound waves, this would be an area of high pressure. This would be an area of low pressure. And that's how it's a compression wave. And then usually you have sort of a neutral line, an equilibrium line down the middle somewhere. The other phrases that we use to kind of talk about this, wavelength, amplitude, frequency, and speed. Now, you've already talked about frequency. Frequency is related to period. This funky looking thing is the Greek letter nu. Nu is how you actually spell that, Nu. It's a lowercase n, basically in Greek. You will see it used as this letter, or you will see it used as the kind of cursive F letter. They're both correct. It does not matter. This one, the Greek letter nu, is more classically used. However, it's harder to type, and a lot of students find it confusing because it looks like a lot like a V. And so sometimes you'll see in high school physics books, sometimes they use an F, sometimes they use nu. So I tend to use nu just because that's what I'm used to, but I try to kind of use both of them. So frequency, again, is a phrase of how often, how many times that wave would pass. A great way to think about frequency is like how many crests are passing in a certain amount of time. So if you think of this wave moving through space and I clap every time a crest comes past, we can count how many waves pass in a second, and that would be a measure of frequency. Again, frequency, and period are related to one another. And so period is just how long, frequency is how often. And that's a subtle but really important difference for physics students to understand, to try to get the hang of that. Again, frequency is a measure of how long does it take for a single wave to pass. Frequency is more like how many waves will pass in a second in a certain set amount of time. Wavelength is a little bit easier. Wavelength is literally what it sounds like. How long is the wave? And that's defined as a couple of different ways. One of the easiest ways to define it is the distance from crest to crest. If you've got that, is a really easy way to measure wavelength, high spot to high spot. You can also measure a complete cycle. And here's what this looks like. It's from equilibrium through a crest, through a trough, and then back to equilibrium again. This is also wavelength. This red line and the distance between this green dot and this green dot are both considered to be wavelength, and they both work. You can use either one depending on what's more convenient for the stuff that you're trying to measure. So like when you're trying to do wavelength measurements and say like the little online simulation, sometimes going crest to crest is easier, just depending on what it is. But that's wavelength. How long is the wave? And again, that's going to be in meters because it's just a length. Amplitude. Amplitude, as we mentioned this before, is a measure of energy. How much energy did it take to create this wave? And that is the distance from equilibrium, from the center point, to the crest, or from equilibrium to the trough. They should be symmetrical. It is not the total height from crest to trough. So it's from middle and up. So that's amplitude. And again, that's a measure between, that's a kind of a measurement of how much energy it is that's in there. Different types of waves express amplitude a little bit differently. So for example, sound waves express amplitude in the sense of loudness, as opposed to light waves express amplitude in terms of brightness. So again, how much energy did it take to create that wave? Wavelength and frequency have different things that they do as well. And then speed is how fast does it travel through the medium, or if it, in the absence of medium, if it's an electromagnetic wave, but literally how fast does it cross space is what we're talking about. That's what speed is. Speed and frequency are not the same thing, and speed and period are not the same thing. Frequency is how often is it happening. So sometimes people will say, well, how fast is it? This is a different meaning of fast. Okay, fast can be this, but if it's going across from left to right slowly, that could be a high frequency with a low speed, as opposed to a high frequency with a high speed. Literally going back and forth, that's a high speed. It was the same rate of snapping, the same frequency, but how quickly did it go across the space? That's the concept of speed. Speed is still distance divided by time. Speed is still distance divided by time. In this particular case, it's not wavelength times frequency. Yeah, it is. It's distance divided by time. How far did it go and how long did it take to get there? It's d times t, but remember that in this case, frequency is 1 over time. So it's literally wavelength, which is distance, how long is the wave, and it's times frequency. So it's kind of an interesting relationship between those two. So again, the couple of key takeaways between here. Cat. Amplitude is related to energy. Again, how big or how tall are those crests? Wavelength and frequency are related to one another, and I'll get to that on the next slide. But wavelength is the distance from crest to crest, or from trough to trough, or the time for the length of a complete cycle. Again, from equilibrium to top to bottom and back to equilibrium again would be another way to define wavelength. Frequency is how often is it happening? Period is how long does it take for one to happen? It's literally just a time. And then speed is crossing space. Literally how long does it take to get from left to right? Let's see if I can get my last slide or so. Last couple of things on here. Almost done. 2 slides left. Move that over there. Okay, so with these couple of things, to take a look at an example of applying it to a pair of waves that's on here. You've got a blue wave and a red wave, so you can kind of see the difference between them. So amplitude, you can tell between the two of them, which one's the larger amplitude wave. Is it the red wave or the blue wave? It's the red wave, obviously, because it has a much taller distance from here to here. The blue wave is a little short amplitude. This one is a much taller amplitude. With wavelength, again, take a look at what the wavelength is. It's from trough to trough, or from crest to crest. Or again, you can go from, if I can get it to start writing again, come on, give me my pen. Give me my pen. You can go from equilibrium through a trough to a crest and back to equilibrium, one full waveform. It's one of those. It's the same wavelength. This one, the red one, has a much longer wavelength. If you take a look at the number of units it takes, the blue one is a lot more waves versus the red one literally has, two full wavelengths on here, as opposed to the blue one has one, two, three, four, five, six, 7 wavelengths to this spot, right? And this one has literally 1, 2 wavelengths in the entire same distance. So red one is a long wavelength and the blue one is a short wavelength. Okay, frequency. Frequency is a measure of how often, sort of a measure of how quick is that snap. If you think of each one of these little units, can you see these units kind of along the top here? Think of each one of those units as being a second or something like that. If we think about this length of time, how many times are we going to snap if we snap every time a crest gets there? Well, if we snap every time a red crest gets there, it's going to be like 1, 2, 3, and we're done. If we snap every time a blue crest gets there, it's like that. It's quite a bit faster. That's that concept of frequency. How close together, not lengthwise, but time-wise, I guess, are those different little crests. Units of frequency are a little bit funky, and I want to mention this one. Okay, so frequency is the same thing as saying 1 over, sorry, I wrote this wrong, time, these two are inversely related to one another. If this is in seconds, time or period is in seconds, the units of this is 1 per second. It's a really weird unit to use. And so you'll see it written like this as a per second. This is the same meaning in exponential notation. To the -1 power means 1 over. Anytime you have a negative exponent, it's over that particular value. So this is also called a per second. This is a per second, and this is a per second. It's more commonly referred to by its nickname by the dude that studied sound, which is this other guy over here, and it's the one that has the HZ to it. That is the unit right there. That's called hertz. 1 Hz or a hertz equals literally 1 per second. These are the same unit. So they mean the same thing. It's kind of like Newton in a meter second or a kilogram meter per second squared. It's another name for the same exact bit. So again, hertz is commonly used, but hertz and per seconds are the same thing. Periods, again, is in seconds. The relationship between period and frequency is 1 over. They're inversely related to one another. And then lastly, speed is in the typical units of speed, meters per second, distance divided by time. So you can either get speed by doing wavelength, which is, I gotta get the right letter. Okay, I don't think I did this on the other page. The Greek letter for wavelength, there's a really funky looking Greek letter for it, which is the Greek letter lambda. So the letter for wavelength right here is this one. That is the Greek letter lambda. You can go look it up, A-M-B-D-A. And then the Greek letter for frequency is nu. This is the letter NU. These are both lowercase letters. This is a lowercase L. This is a lowercase n. And you're like, they don't look anything like English letters. I know. Deal with it. Different alphabet. So anyway, those are the 2 Greek letters that we've got. So when we talk about speed or velocity equals lambda times nu, wavelength times frequency. It's kind of a cool thing. Or we can say it's the same thing as saying it is wavelength divided by time. And this is period down here. These are the same thing. Remember, meters per second. The unit of this is a per second. So if you do meters times per seconds, you get meters per second. Or if you do meters divided by seconds, you get meters per second. So that's how we calculate speed or the velocity of any particular wave. So again, speed is how fast it crosses the area, goes left to right. Frequency is how often is it, how many little crests per second are there. Period is how long it takes for one single crest to go by. It's just how little we time it. And then wavelength is how far apart of these little crests are. When we're talking about electromagnetic radiation, there's some things that we can kind of pull together, some consistencies that are kind of nice that allow us to see the relationships between frequency, wavelength, and speed. So again, frequency, the letter is this, or again, it could be that one as well. Wavelength is the Greek letter lambda, and then speed is velocity typically. And this works for pretty much any type of wave that you want to refer to. With electromagnetic radiation, there's an additional thing that we can use, and it's kind of nice. The speed of electromagnetic radiation, it doesn't matter what type it is, any of these types that are on this diagram up here, all electromagnetic radiation goes at the same speed, which is 3 times 10 to the 8th meters per second. This is a universal constant. It's been known for a long time. It's usually presented this way in 1 sig fig. It can be written in 2.997 or 2.9978 or something like that. Don't let this limit your sig figs, but that's just a really commonly used abbreviation for the speed of light. And because it's such a constant, and it appears to be a really important physical constant in how the universe works, it's given its own letter, which is a lowercase c. You've seen that in something before. Einstein's little equation that he uses, E equals mc squared. That's the c that they're referring to. This c right here is the speed of light. This is energy equals mass times the speed of light squared. That'll mess with your mind if you want to think about that for a while. But that's that lowercase c. It's the speed of light, the constant for the speed of electromagnetic radiation. It's incredibly fast. 300 million meters in 1 second. That's how quickly light crosses space. By comparison, if you're talking about typical sound waves, it's a little bit slower. So typically sound, you're talking about thunder and lightning right here. Thunder travels at about 343 meters per second, as opposed to lightning or light travels at 300 million meters per second. Yes, light is 1,000,000 times faster than typical sound waves. That's why there's such a big difference between when you see the lightning and when you hear the thunder. So when we're talking about speed, there's a consistent relationship with speed that has to do with wavelength and frequency, but the speeds themselves may be different. So again, for all of these kinds of electromagnetic radiation, any of them, including visible light and all the other types that are up here, they all travel at the speed of c, or 3 times 10 to the 8th meters per second. Other types of waves have their own velocities, which we abbreviate with the letter v because they're a little bit different. So water waves obviously travel quite a bit slower than sound waves, different than seismic waves, etc. However, there is one thing that's always true about these, is that if you talk about a particular wave that's going a particular speed, there's always an inverse relationship between wavelength and frequency. And you can see it in this diagram really, really nicely. So when you talk about really short wavelength forms of any type of wave, short wavelengths are high frequency. If you talk about long wavelength forms, they're going to be low frequency if they're going the same speed. And that's the key constant between these particular things, is that as one goes up, the other goes down. So if there's a lot of space between the waves, then typically they're going to come a little bit more slowly, right? If there's only a little bit of space between the waves, they're going to come a lot more quickly. So again, wavelength and frequency are inversely related. That's what this phrase is over here. And again, typically when we're talking about electromagnetic radiation, it's a really easy constant, but a lot of the phenomena we're going to talk about in the next few chapters have to do with moderating or manipulating wavelengths and frequencies and how those get affected as the speed of a wave can sometimes change when it's traveling through different media. So there you go. We've got a lot of different kind of quantities in here. One of the key equation that you need to get, and I want to put it up here in a nice equal even spot just to kind of highlight how important it is, not that one. The key equation that you need to take away from this is written one of two different ways. It's either this one, C equals lambda nu, which is what we're talking about for light, or if you're talking about in general, wavelength times frequency, that there's an inverse relationship. As wavelength goes up and speed stays constant, as wavelength goes up, frequency has to go down. If we know what that speed is, 3 times 10 to the 8th, or sometimes we have to calculate what the speed is, just depending on what it is. You will not need to memorize this number. Okay, there you go. So there is important characteristics of waves, how wavelength, frequency, amplitude, period, all those sorts of things are related to one another. You need to make sure that you're doing the lab simulation that explores water waves, sound waves, and light waves to get some of the ideas of how these different types of things like wavelength and frequency are expressed in different types of waves. So there you go. Have a good one, and enjoy your day, evening, afternoon, whatever it is, your COVID time. And I'll see you in the next time.